Hello, in this recording we'll be going over polynomial functions of higher degree. Our goal is that by the end of this presentation, you'll be able to sketch transformations of polynomial functions, use the leading coefficient test for end behavior, find real zeros and use them as graphing aids, and use the intermediate value theorem to locate real zeros. So here we have two of the key features of a graph of a polynomial function. The first one being is that polynomial graphs are continuous. So on the left-hand side, we see that it has no breaks, holes, or gaps, whereas on the right hand, it does not. Therefore, it is not a polynomial function. Another key feature is that they have smooth, rounded turns. On the left, we see that at the turns, they are smooth, and they don't have sharp corners, whereas on the right-hand side, that would be the case. An example of that would be the graph of the absolute value of x. Here we have some examples of sketching transformations of monomial functions. So one key thing to remember is that odd powers will behave like the function x cubed, and even powers will behave like the function x squared. So for example, 1a, we have f of x is equal to negative x to the power of 5. So since our degree is odd, that means the function will behave like x cubed. And since we have a negative in front of the x, then that sign will reflect the graph across the x-axis. For example, 1b, we have the function h of x is equal to x plus 1 to the power of 4. So since our degree is even, the graph is similar to x squared, and the graph will be shifted 1 unit to the left from x to the power of 4 because of that plus 1 on the inside of the parentheses. So here's another example, f of x is equal to x plus 5 to the power of 4. We see that we have an even degree, so the graph will behave like x squared, or x to the power of 4. And we see that we have a plus 5 on the inside of the parentheses, so that is a horizontal shift. We'll be moving 5 units to the left. In this example, we'll be practicing shifting a graph vertically. So our function g of x is equal to x to the power of 4 minus 7 will behave similarly to the graph x squared, or x to the power of 4, because we have an even degree, 4. Now our constant term, negative 7, will indicate how many units will be shifting downward or upward. So a constant term is a term without a variable. So ours is negative 7. Since it's negative, we'll be shifting downward 7 units. Here is another example practicing shifting the graph vertically. Our function is h of x is equal to 7 minus x to the power of 4. Our degree is even, so it is similar to the function y is equal to x to the power of 4. But now we have a negative in front of the x to the power of 4, so that means our graph will be reflected across the x-axis. Now our constant term, 7, is positive, so that means it'll be shifted 7 units upward. Had it been negative, we would shift the graph y is equal to x to the power of 4 7 units downward. So the constant term in a polynomial function will give us our y-intercept. Now we have the function k of x is equal to 1/4 times x minus 3 to the power of 4. So once again, our degree is 4, so it'll be behaving similar to the function y is equal to x to the power of 4. Since we have a minus 3 on the inside of the parentheses, that'll be a horizontal shift of 3 units to the right. And since we have 1/4 in the front, that means we are vertically shrinking our function by a factor of 1/4. So to summarize what we just went over, polynomial graphs are continuous, meaning they have no breaks, holes, or gaps. They have smooth turns, meaning they don't have sharp corners, unlike the graph of the absolute value of x. And lastly, they are controlled by the degree and by the leading coefficient. Here are some of the key features of the parent functions. So when we have even powers, such as x squared, x to the power of 4, x to the power of 6, that means our graph will have a U-shaped behavior. When we have odd powers, such as x cubed, x to the power of 5, x to the power of 7, our graph will have an S-shaped behavior. One thing to note is that when we have a higher power, that means our graph will be flatter near the origin. So here are the steps for the leading coefficient test. First, we will find the degree, n. We will decide if n is even or odd. Then we will check whether the leading coefficient is positive or negative. Then we use the combination to predict left end and right end behavior. Here are the 4 possibilities of the leading coefficient test. For the first one, this happens when there's an odd degree and we have a positive leading coefficient. Then the left end of the function will go downward and the right end of the function will go upward. For the second possibility, This happens when we have an odd degree and a negative leading coefficient. Then the left end of the function will point upward, and the right end of the function will point downward. Now for the third possibility, this happens when we have an even degree and a positive leading coefficient. Then both ends of the function will point upward. For the fourth possibility, this occurs when we have an even degree and a negative leading coefficient. Then both of the ends of the function will point downward. We notice that when we have an even degree, both of the ends have the same behavior, and when we have an odd degree, the ends are opposite behavior. These examples of the functions show only a portion of the graph, not the entirety, so this is just to demonstrate how it'll behave at the endpoints that we are looking at. So here's a summary of the previous slide. It is important to remember that when a polynomial has an odd degree, then the ends will have opposite behavior. When a polynomial has an even degree, then the ends will go in the same direction or have the same behavior. Now we'll be going over real zeros of polynomial functions. It is important to remember that the zeros of a function are the points at which the function crosses or touches the x-axis. So the degree of the function can tell us how many real zeros we have. So the function f will have at most n real zeros. For example, if we have a polynomial of degree 3, then the most real zeros we can have is 3. Now the degree can also tell us how many turning points, or how many relative minima or maxima the graph of f will have. So the graph of f will have at most n minus 1 turning points. Another way that we can describe turning points are the points at which the graph will change from increasing to decreasing, or vice versa. So now we have some equivalent statements for real zeros. So we have f a polynomial and a real number. So for the first statement, x is equal to a is a zero of the function f. For number 2, we have x is equal to a is a solution of the polynomial equation f of x is equal to 0, or f of a is equal to 0. For number 3, we have x minus a is a factor of the polynomial f of x. For number 4, we have the point a comma 0 is an x-intercept of the graph of f. So here's an example of finding the real zeros of a polynomial function. So we're given the function f of x is equal to negative 2x to the power of 4 plus 2x squared. So the first step is to set f of x equal to 0. So we have negative 2x to the power of 4 plus 2x squared is equal to 0. Now we can factor out the negative 2x squared. So now we'll have negative 2x squared times x squared minus 1 is equal to 0. Now we see that x squared minus 1 is the difference of squares. That means that we can factor the x squared minus 1 further into x minus 1 times x plus 1. So now that we have the term negative 2x squared times x minus 1 times x plus 1, we can set each of these individual parts equal to 0. So negative 2x squared equal to 0 will imply x is equal to 0. X minus 1 equal to 0 will imply x is equal to positive 1. And x plus 1 equal to 0 will imply that x is equal to negative 1. So our three zeros are at x is equal to negative 1, x is equal to 0, and x is equal to 1. So using our degree 4, we'll know that the most turning points that the function f can have is 3, because n minus 1, or in our case 4 minus 1, will give us 3. So the multiplicity of a 0, or how many times that 0 is repeated, can tell us the behavior of that 0. So when we have an odd multiplicity of that 0, that means that the graph will cross the x-axis at x is equal to a. When we have an even multiplicity, that means that the graph will touch the x-axis at x is equal to a. Now we're given an example to sketch a polynomial graph. So first off, we're given the function 3x to the power of 4 minus 4x cubed. So we have an even degree of 4 and a positive leading coefficient of 3. So that means that the end behavior of the function will be the same on both ends, and they will both be pointing upward. So now to find the real zeros, we can factor the function. So we can factor out an x cubed, so we'll have x cubed times 3x minus 4. We can set each of those portions equal to 0, and we'll see that x is equal to 0 and x is equal to 4 over 3. And both of those have an odd multiplicity, meaning at those points, the function will cross the x-axis. Now we can plot additional points by using the intervals created by the zeros. So we have negative infinity to 0, 0 to 4 over 3, and 4 over 3 to positive infinity. So for the first interval, negative infinity to 0, we chose the x value negative 1. So f of negative 1 will give us 7. So we'll have the point negative 1, comma 7. So now for the second interval, we had 0 to 4 over 3. So we chose the x value 1. So f of 1 will give us negative 1. So we'll have 1, comma negative 1. And for the last interval, we chose the x value 3 over 2. So f over 3 over 2 will give us 27 over 16. So the point will be 3 over 2, comma 27 over 16. So now we can draw the graph. So we start at the upper left because the graph rises on the left. We cross the x-axis at x is equal to 0 and at x is equal to 4 over 3 because both zeros are odd. And then we can use the plotted points to shape the curve and finish rising to the right. So here's another example of graphing a polynomial. So we're given the function f of x is equal to negative 2x cubed plus 6x squared minus 9 over 2x. So we have a negative leading coefficient and an odd degree. So that means that the end behavior of the function will be the opposite on both ends, and it will rise to the left and fall to the right. So now to find the zeros, we can factor once again. So we can factor out a negative 1/2 x, so we'll be left with negative 1/2 x times 2x minus 3 squared. So for the first 0, we'll have x is equal to 0, and for the second one, we'll have x is equal to 3 over 2. Now for x is equal to 0, we have an odd multiplicity, and for x is equal to 3 over 2, we have an even multiplicity. So that means for x equal to 0, the function will cross the x-axis, and for x is equal to 3 over 2, the function will turn around. It'll touch the x-axis and turn around. Now we can construct test intervals from the zeros. So we have negative infinity to 0, 0 to 3 over 2, and 3 over 2 to positive infinity. So for negative infinity to 0, we choose the x value negative 1/2. So f of negative 1/2 is equal to 4, and we're given the point negative 1/2, comma 4. For the test interval 0 to 3 over 2, we choose the x value 1/2. So f of 1/2 will give us negative 1. So we'll have the point 1/2, comma negative 1. Now for the last interval, we choose the value x is equal to 2. So f of 2 will give us negative 1. So we'll have the point 2, comma negative 1. Now building the sketch, we'll add the intercepts first, so 0, 0, and 3 over 2, 0. Now at x equal to 0, the function will cross because its multiplicity is odd, and at x is equal to 3 over 2, the function will touch because the multiplicity is even. So then, using the extra points from our test intervals, we can use those points to guide the curve, and we'll have the final function. Now we'll be going over the intermediate value theorem. So the core idea behind this theorem is that if we're given 2 points, a, comma f of a, and b, comma f of b, where f of a is not equal to f of b, then for any value d that is between f of a and f of b, there exists a number c that is between a and b, such that f of c is equal to d. So this tells us that on the interval a, b, f will take on every value between f of a and f of b. Now this is important because this theorem will help us locate real zeros of polynomial functions. So if the function is negative at one x value and positive at the other, this will guarantee that the function will cross the x-axis somewhere between those 2 points, and that'll mean that there is a real zero between that interval. So for example, we have the function f of x is equal to x cubed plus x squared plus 1. And we're given the interval negative 2, comma negative 1. So at f of negative 2, we have the value negative 3. And for f of negative 1, we have the value 1. So they have opposite signs. So that means that the function crosses the x-axis somewhere between x is equal to negative 2 and x is equal to negative 1. So in order to guarantee a zero between a and b, f of a and f of b, or our y values, must have opposite signs. If they have the same sign, then this theorem is inconclusive and we cannot guarantee a zero between those 2 values. So here's some more practice regarding the end behavior and real zeros of polynomials. So for the first example, we have the function f of x is equal to negative 3.6 times x to the power 5 plus 5 times x to the power 3 minus 1. So we have a leading coefficient of negative 3.6, so that is negative, and we have an odd degree of 5. So that means the end behavior will be opposite on both ends. So that means the graph will rise to the left and fall to the right. For our second example, we are told to find the real zeros. So we have g of x is equal to x cubed minus 12x squared plus 36x. So first we can factor out an x. So we have x times x squared minus 12x plus 36. Now inside the parentheses, we see we have a perfect square trinomial. So we can further factor that out, and it'll be x minus 6 squared times x. So now we can set each of those portions equal to 0, and we'll have x is equal to 0 and x is equal to 6. So at x is equal to 0, we have a multiplicity of 1. So that means that the function will cross the x-axis at x is equal to 0. And at x is equal to 6, we have a multiplicity of 2. So that means that the function will touch the x-axis and turn around. So now we're just going over the key rule of the multiplicity again. So if a 0 has odd multiplicity, the graph will cross the x-axis. And if a 0 has even multiplicity, then the graph will touch the x-axis. So here we have a visual of our function y is equal to x times x minus 6 squared. So at x is equal to 0, we had an odd multiplicity, so we see the function crosses the x-axis. Now for x is equal to 6, we had an even multiplicity, so that means that the function touched the x-axis and turned around.